Imagine trying to measure the height of objects in a room without a consistent floor to stand on. Your measurements would be all over the place, making it impossible to accurately compare anything. In the world of electronics, a similar principle applies to voltage. For a microcontroller to reliably interpret electrical signals and operate predictably, it needs a stable and universally agreed upon reference point for all its measurements. Microcontroller ground pins establish this essential electrical reference by providing a common 0-volt potential across the entire circuit. This means that every other voltage within the system, whether it is an input signal, an output signal, or the supply voltage, is measured relative to this specific ground potential. Without this shared reference, the microcontroller would be unable to accurately differentiate between various voltage levels, leading to unpredictable or erroneous operation. The fundamental reason for needing a common ground lies in how electricity behaves. Voltage is not an absolute value. Instead, it represents the asterisk difference in electrical potential between 2 points. Current, in turn, flows in a complete loop, moving from a higher potential to a lower potential and back to its source. The ground pin effectively serves as the return path for this current and the designated 0-volt point. When you connect the negative terminal of your power supply to ground, you are defining this zero reference. All the microcontroller's internal circuitry, and any external components connected to it, relying on this consistent baseline to ensure that a 5-volt signal is indeed 5 volts higher than the defined ground, and not some fluctuating, ambiguous value. To effectively establish this reference in practice, connect all the ground pins of your microcontroller to a common ground point. This usually involves connecting them to a dedicated ground plane on a printed circuit board or a robust ground bus wire in simpler setups. It is equally important that all other components communicating with the microcontroller, such as sensors, actuators, or communication modules, also share this exact same common ground. This ensures that when a sensor sends a signal to the microcontroller, both components are measuring that signal against the identical 0-volt benchmark, allowing for accurate data interpretation and reliable system performance. Beyond simply connecting wires, savvy engineers often utilize a large, uninterrupted copper area on a printed circuit board known as a ground plane. This design choice provides a very low impedance path for return currents, minimizing unwanted voltage drops and electromagnetic interference, which can otherwise introduce noise and instability. For sensitive applications, you might also encounter separate analog ground, often labeled a GND, and digital ground, DGND. While these are often tied together at a single point to maintain a unified system reference, separating them initially helps isolate sensitive analog signals from the noisier digital switching currents before they merge. Ultimately, the microcontroller's ground pins are for more than just a connection point for the negative side of the battery. They are the electrical bedrock upon which all measurements are made and all operations are founded. By providing a stable, common 0-volt reference, they enable accurate voltage measurement, ensure predictable current flow, and create a reliable electrical environment crucial for your microcontroller to perform its intended functions seamlessly and consistently.